Hi guys, in the last lecture what we did is we covered the basic laws of electromagnetism. There we saw first of all Faraday's law, and we saw the necessary condition for Faraday's law, which was set of conductors, a presence of a magnetic field and relative variation. Based on relative variation, we classified into two categories. One was dynamically induced EMF or motional EMF, okay, which we called as EMF is equal to BLV. Then we classified next was statically induced EMF, which was nothing but EMF is equal to minus N d phi by dt. Here the conductors are static with respect to magnetic field. Okay. The minus sign here signifies the Lenz law. Lenz law states that induced EMF opposes the cause of induction. Then we saw self-induced EMF and mutually induced EMF. Self-induced was when the current carrying coil induces an EMF in the same coil. Mutually induced was when the current carrying coil induces an EMF in the other coil which is magnetically coupled to this coil. Then we saw dot notation. To represent the polarity of EMF induced in a coil, we use dot convention. And last, we saw Lorentz force law, that is the force experienced by a current carrying conductor when it is kept in a magnetic field. Okay, in this lecture we will be looking at some of the magnetic materials and the magnetic circuits. So first of all, what is a magnetic circuit? A magnetic circuit is nothing but it is a device in which the flux flows in a closed path. Like in an electrical circuit, usually the current flows in a closed path. Similarly, in a magnetic circuit, the flux will flow in a closed path. So here we are talking about the magnetism. The basic Maxwell's equation for magnetism are integral H dot dl is equal to current enclosed, that is J dot ds. Similarly, integral B dot ds equal to 0. This is the Gauss law for magnetism. This is the Ampere circuital law. So magnetic flux density and the magnetic field must satisfy these two criterion for being classified as a magnetic field. Okay. So our aim in this lecture is to simplify this sort of magnetic circuits and represent them in electrical form. Okay. Because in network theory we study a lot of method to analyze the electrical circuits. If we can somehow convert this magnetic circuit into an electrical circuit, then my analysis would be simpler. Okay. So here we have shown a magnetic circuit. Here this winding has n number of turns. The current I is going into the winding. This the path of the flux. Okay. The path taken by the flux has a total length LC, which is called as mean core length. It is nothing but length of the path traversed by the flux. Then the cross sectional area is AC, permeability of the core is mu. Okay. Now we can say that the flux induced will be integral B dot ds. Okay. And the SI unit of flux would be Weber. This magnetic flux density SI unit is Weber per meter square or Tesla. This will be the flux induced. Now, if we assume that the magnetic flux density is perpendicular to the cross section area, this is my cross section area. If magnetic flux density is like this, it is perpendicular to the area, or we can say it is in the same direction as the area vector. Remember, area vector is always perpendicular to the area. So if this is my area vector, this is my magnetic field, the dot product would be B into A directly. Okay, because they are in the same direction. So B dot A will be B into A. So this flux becomes nothing but BC into AC. BC is the magnetic field developed in the core. AC is the cross-sectional area of the core. This is the flux developed inside the core of the magnetic circuit. Now, we define a term called as MMF, which is magnetomotive force. Okay. Like in electrical circuits, we define a electromotive force. It is the main reason behind the flow of current, that whenever there is a EMF and there is a closed path, a current will flow in the circuit. Similarly here, whenever there is a MMF and a closed path is available for the flow of flux, the flux will flow inside the magnetic circuit. Same logic applies here. Okay. Now, this flux is being developed due to this current flowing in the winding. Okay. Flux is only being developed because of the current flowing in the winding. That means the MMF should contain the term current. Okay. Because current is responsible for the development of flux. So MMF is nothing but number of turns into current, Ni. Okay. Total number of turns in the winding, and I is the current. We know current enclosed is nothing but, by Ampere's law, H dot dl. Current enclosed is H dot dl, which is Hc into Lc. Here also I am assuming that H lies along the magnetic path. Okay. See, the magnetic path is shown like this. H will also be developed in the same direction. If you allow the right hand rule, then curl your fingers in the direction of winding like this. Then the direction of thumb will give you the direction of magnetic field like this. So in a closed path it will flow like this. That's why H and dl in the same direction, Hc into Lc. Now we know Hc will be nothing but Bc by mu. So I can say F is equal to Bc Lc by mu. Bc is nothing but phi c Lc by mu Ac. So what I can say, MMF is equal to flux into reluctance, where reluctance is nothing but Lc by mu times Ac. Okay. So this is the same relation as in electrical circuits we have Ohm's law. There V is equal to IR. Here flux is equal to MMF into reluctance. There resistance was given by rho L by A. Here reluctance is being given by L by mu A. Just the resistivity is replaced by reciprocal of permeability. So we have arrived at a similar relation to the electrical circuits. Okay. So remember these terms. MMF is nothing but, it is the product of number of turns and current, that is we can call it as ampere turns. Then flux is being developed in the winding due to production of a magnetic field. Phi is the flux and R is the reluctance of the magnetic core. Next, let us consider another magnetic circuit which has a air gap in the magnetic path. Here what I have done is, I have taken a part of the magnetic material out so that we have a air gap between this path. So let us see what is the impact of air gap in the magnetic path. The thing is, in the core, the magnetic field will be phi upon area of cross section of the core, but in the air gap, magnetic flux density would be phi upon Ag. Okay, Ag is the cross sectional area of the air gap. Now MMF would be, we saw in the previous slide, MMF was H into L. So here H core into L core plus H air gap into G. G is the length of the air gap. Okay, air gap length is G. This is my MMF. Now we can replace this by magnetic flux density. F can be written as Bc by mu c into Lc plus Bg by mu naught into Okay, we have replaced the magnetic field intensity by the magnetic flux density. Now we know B is phi by area. So it is phi by LC by mu C into AC plus G by mu naught into AG. This will be my relation between flux and the MMF. So what I can say, R equivalent or equivalent reluctance is LC by mu C into AC plus G by mu naught into AG. This will be reluctance of the core plus reluctance of the air gap. So since the reluctances are being added, what I can imagine in electrical circuit terms is, it is a series circuit. So how can I draw the electrical equivalent? To draw the electrical equivalent, we will consider a voltage source. Here the voltage source is nothing but MMF. And we will have two reluctances represented as resistances, RC and RG. Here we will have a flux phi. Okay, this is the flux phi in the flowing in this circuit. MMF will be equal to phi into RC plus RG. Now see what happens. While we have introduced the air gap, we have an additional reluctance RG. That means by introduction of the air gap, reluctance of the magnetic path increases. So in whatever machines we will be studying, whenever there is a air gap between the stator and the rotor, it implies that the reluctance of the magnetic path increases. And if we assume, since F is equal to phi into R equivalent, if we assume constant flux, then increase in reluctance will cause increase in MMF, which in turn causes increase in current. Okay, that means in the machines, if we increase the air gap, the reluctance of the magnetic path increases, which causes an increase in the current for the constant flux. This current is called as magnetizing current. Why magnetizing current? Because this current is responsible for magnetizing the core or making the core magnetic, that is developing a flux inside the core. Making it magnetic just means inducing a magnetic field inside the core. This current is responsible for such behavior, hence it is called as magnetizing current. So remember, as air gap is increased in an electrical machine, magnetizing current increases for a constant flux. Now let us look at a problem based on this concept. So here we have 3 limbs in total, but the thing is, permeability of the core is infinite. Infinite permeability, what it implies is, entire flux is developed in the core. Why? We know reluctance is nothing but L by mu A. If mu tends to infinity, it means reluctance tends to 0. And in electrical circuit terms, it means it is short circuit. And we know the entire current flows through the short circuit. Hence, entire flux will flow through the path which has the infinite permeability or the 0 reluctance. So entire flux will be flowing in this path. It implies there is no flux leaking into the air, or leakage flux is 0. So infinite permeability is the ideal case, so that there is no leakage of the flux from the core. So due to this, the reluctance of all the limbs will be 0. Just the reluctance of air gap will be non-zero. Due to this G1, the reluctance, let us call it as R1, will be G1 by mu naught A1. Similarly, due to G2, reluctance will be R2, which is G2 by mu naught A2. Now if you see, the flux being developed here will be going like this, and it will be going like this. So in electrical circuit terms, if you see, the flux is being divided into two paths. That means these both are connected in parallel. So how we will draw the electrical equivalent circuit? Ni, then we will take R1, then we will take R2. These two will be connected in series because flux is being divided between the two. In the previous case, since flux was common in both the reluctances, they were connected in series. Okay, similar to the electrical circuits case, Whenever the current is same in two elements, they are connected in series. If current is divided, they are connected in parallel. So this is the basic concept of the magnetic circuit. So here what we need to remember throughout the course of electrical machines is the three terms: MMF, flux and reluctance, and the relation between these three. Now let us see what kind of materials do we use for the construction of electrical machines. What kind of magnetic materials do we use? So first question arises, what is meant by magnetic materials? The thing is, the materials that can be magnetized, or magnetization in simple terms means the materials in which a magnetic field can be induced. Okay, materials which can be magnetized are called as magnetic material. That means I want to induce a magnetic field. Magnetized means magnetic field can be induced. The thing is, the other materials are called as non-magnetic materials, but essentially they are not non-magnetic, which means the magnetic field is induced in any kind of material. Then how do we classify, or how do we separate the magnetic materials from the non-magnetic materials? The basic criterion is the strength of the magnetic field. If the magnetic field induced in the material is strong, then it will be classified as a magnetic material. If the induced magnetic field is weak, then it is classified as the non-magnetic material. Okay. Strong magnetic field means magnetic material, and weak magnetic field means non-magnetic material. Okay. So now let us see in what all categories can we divide the magnetic materials and what has a specific properties. First is diamagnetic material. The thing is, the materials that are called as diamagnetic is in which the magnetic field is not persistent. That is, magnetism only persists when an external field is applied. Okay. Non-persistent means when you remove the magnetic field, the magnetic behavior goes away. So magnetic behavior is non-persistent. It does not persist for a long duration. Okay. And here the induced magnetic moment, like electrical dipole moment, we have magnetic dipole moment is small. Here the induced dipole moment is small. And the main thing, or the most important thing about the diamagnetic material is direction of magnetization is in the opposite direction to the magnetic field. See, before magnetic field is applied, the dipoles will be oriented in random directions like this. But as soon as magnetic field is applied, where H is not 0, they will be oriented in opposite direction. Magnetic field is applied towards right, dipoles will get oriented in the reverse direction, opposite to the magnetic field. This is the property of the diamagnetic materials, that direction of magnetization is opposite to the direction of magnetic field. Those materials are called as diamagnetic. Why it is opposite? It is opposite due to the orbital motion of the electrons. Some of the diamagnetic materials are copper, gold, germanium, silicon, diamond. These sort of materials are diamagnetic in nature. Moving on to the next type is paramagnetic. They have the same characteristics as those of diamagnetic. That is, the magnetism here also is non-persistent. Okay. That is, as soon as we remove the magnetic field, the dipoles will rearrange themselves along the random direction to make the magnetization 0. That is, they won't have any specific direction if you remove the magnetic field. That is what is called as non-persistent magnetism. Okay. So, before magnetic field is applied, when H is 0, they will be oriented in random directions. But as soon as you apply H, let us say towards the right, here the dipoles will be oriented in the same direction. The only difference between paramagnetic and diamagnetic is dipoles are oriented in same direction for paramagnetic material and dipoles are oriented in opposite direction for the diamagnetic material. Okay, so paramagnetic materials are generally attracted by the magnetic field. Okay, if we apply a magnetic field, paramagnetic materials are attracted towards the magnetic field and diamagnetic materials are repelled by the magnetic field. This point also you must remember, it is attracted by the magnetic field. Okay, diamagnetic will be repelled. So some of the materials that are my paramagnetic materials are potassium, oxygen, tungsten, Fe2O3, FeCl2. Such sort of materials are paramagnetic in nature. Next, let us move on to the ferromagnetic materials. Ferromagnetic materials is when we apply a magnetic field, all the dipoles are oriented in the direction of the magnetic field and it has strong magnetization. The thing with paramagnetic and diamagnetic is magnetization was weak. But in ferromagnetic, magnetization is pretty strong and in the same direction as field. Okay, same direction as the external field applied is my ferromagnetic. One more essential difference is the spontaneous magnetization or the residual magnetism. In ferromagnetic material, there is a hysteresis curve. So that means if we draw the hysteresis curve, it is something like this. Okay. This middle line here in the hysteresis curve represents what happens or what behavior is followed when we magnetize a freshly prepared sample that hasn't been magnetized ever before. And the upper and the lower curves represent the loading and the unloading characteristic. Now if you see, generally we say B is equal to mu H. That means if H is 0, then magnetic flux density should also be 0. But if you see here, when H is 0, it has a residual magnetic flux density Br, and here also it is Br. Okay, let us say minus Br. Such sort of materials are called as ferromagnetic materials, which have spontaneous magnetization. That means which can be magnetized or which remain magnetized even in the absence of the magnetic field. Those materials are called as ferromagnetic material, and the residual magnetic flux density is called as residual magnetization. And if you wish to reduce the magnetic flux density to 0, you have to apply this much H. It is called as Hc, or it is called as coercive force. Coercive force is nothing but the magnetic field required to be applied to make the magnetic flux density 0 in a ferromagnetic material. Okay, again I am repeating, it is the amount of magnetic field intensity required to make the magnetic flux density 0 in a ferromagnetic material. So these are the characteristics of a ferromagnetic material, and these are the materials that are strongly magnetized in the presence of a magnetic field. So such sort of materials are usually used to construct the electrical machines. As we will see in the transformers, generally silicon steel is used, which is itself a ferromagnetic material. Next type of materials are ferrimagnetic. Okay, here what happens is, when magnetic field is applied, the adjacent dipoles are oriented in opposite direction. Okay, but the thing is, the magnitude of dipole moment is not equal. If it has a magnitude of 10, it will have a magnitude of 5. So net will be a magnitude of 5. So it means adjacent dipoles are oriented in opposite directions, but the magnitude of both the dipoles that are oriented in opposite direction is not same. That is why it leads to a net magnetization but this net magnetization is generally smaller as compared to the ferromagnetic material. In ferrimagnetic, the magnetization is smaller as compared to ferromagnetic because adjacent dipoles are oriented in opposite directions. They are not oriented in the same direction. Then why should we go for ferrimagnetic materials? The thing is, they have high resistivity. Okay, their resistivity is very high. And as we will study later on, eddy current losses are directly proportional to frequency square by resistivity. So if you increase the frequency, eddy current losses will increase. So how to reduce them is by using the materials which have higher resistivity, that is we will use ferrimagnetic material, or they are called as ferrites. Okay, we will use the ferrites. So that is why in transformers with low frequency transformer, ferromagnetic materials are used, and with high frequency transformers we use the ferrites or the ferrimagnetic material to reduce the eddy current losses in the transformer core. Okay, so let us summarize what we learned today. We first saw MMF. MMF is equal to N into I. Then we saw flux. Flux is B into A. Then we saw reluctance, which is L by mu A. And we saw the relation as per the Ohm's law also. F is equal to phi into R. Similar to the Ohm's law, which is V is equal to IR. F is the magnetomotive force, V is the electromotive force. Then we saw introduction of air gap makes equivalent equal to R core plus Rg. So reluctance increases. That means the current will also increase for a constant flux. Then we saw types of magnetic material. First one was diamagnetic, in which dipoles are oriented in opposite direction to the magnetic field. Then was paramagnetic. Dipoles are oriented in the same direction, but in both these material magnetization is small. So paramagnetic materials are attracted by magnetic field, diamagnetic are repelled. Then we saw ferromagnetic. They have residual magnetism and dipoles are oriented in the same direction to the magnetic field. So they will be strongly attracted by the magnetic field. They have strong magnetization. And last we saw ferrimagnetic, in which dipoles are oriented in opposite directions. So net magnetization is small, but these are preferable because of higher resistivity, so reduced eddy current losses. In the next lecture, we will be starting with the transformer. These are the basics of the materials that are used in the machines and the basic laws of electromagnetism. So we will be starting with our first machine, that is transformer.